Good morning, everyone. I hope you had a good Easter. As you can see, we're starting a new topic, and it's not a particularly difficult topic. DNA, we've been skirting around it for quite some time with our other topics. I'm only going to go through a couple of things in this video. So I don't suggest you start here. I suggest you start with some of the pages of the PowerPoint, and then hopefully some of the more tricky things will make a bit more sense after this video. So one thing I want to take a look at is the sugar part of our nucleotides. It's not quite complete, this drawing here, and you can see it's quite an odd way of drawing things, but it helps us to see what's going on and helps us to draw the polynucleotides that we'll start making in a minute. So one thing that might be a little confusing is where we put things. So the base will go here on the sugar. So that becomes our carbon 1. You need to be aware of how this leads to our other labels. You'll see quite a few of the labels in the booklet. 2, 3, 4, and 5. So take care. This looks like a 5-membered ring, but one of them is, of course, an oxygen, and carbon 5 is actually sticking out of the ring. Now, things stick on, the phosphate group sticks onto carbon 5 when we draw the nucleotide. The reason for that is if we were to try and make a polynucleotide by sticking these together, we'd stick the new one at position 3. So position 5 is actually where we'll draw our first phosphate group. And eventually we're also going to want to start putting on a base, so we're going to put some guanine on. That's guanine there. Of course, you'll remember your guanine has that NH bit, but that's the bit that sticks to here. So in a minute, I'm going to scrub that H out. So let's see how well this goes. We're going to use this, and I'm going to draw some new bits on. So in a minute we'll put our guanine there. This drawing I've actually borrowed off page 12 of your booklet. So we just need to know what else needs to be put on to the sugar. We need these. And we need this. And we have an O. And for the time being, we've got a H. That's number 3, so that's where we'd be putting more things later on. Now we've got this. This is a carbon, H2. And of course we've got a bit more to add there to speed things up. I've got a few of them here. Yes, I do. So let's put all those together. There we are, nicely annotated. So now I can stick the phosphate on it. Now the phosphate, this isn't quite drawn the same way as you have it in your booklet. So go with what's in the booklet, but for ease I'm going to just add that on. Okay, so that's the phosphate bit. And I'll put this in slightly the wrong place. And here's my guanine with the bit chopped out as promised. Ooh, that was working a minute ago. There we are. That's brought it to the top. Okay, so that is the nucleotide, one of them. If I wanted to make a polynucleotide, I'd be doing a condensation type polymerization using this and the phosphate group of another one, which, as I say, isn't quite drawn like this. That's just one I've been able to get from the PowerPoint. So go with what's in the booklet. So that's how the numbering links to things. We then stick loads more on number 3 to make the chain, the polynucleotide chain. The other thing I wanted to go through was what happens when we put some cisplatin in here. That's another little fact you need to know. We've met some of it already. So what I'm going to do is just copy this. Now cisplatin does what it does because it can attach to 2 DNA bases. And those two can be on the same chain or they can be on different chains, but either way, by attaching to two, it bends the whole structure, it changes the whole thing, puts a kink in it. So it will be able to change the shape, provided it's the right shape to stick onto multiple of these, then it would be the right shape to cause some damage to the DNA. So here are my two different forms of it. So we'll look at this form first, and it's a bit small. Let's see if we can make it bigger. There's cisplatin, 2 chloride ligands, and a +2 oxidation state on the platinum. So you can, of course, use your transition metals knowledge to tell me why this is a solid that can be given to a patient, not a solution. In the body, these chloride ligands can disappear and be replaced with some waters initially. But as you can see, nitrogen forms quite a good dative bond to cisplatin. So our nitrogen in our guanine will be able to bond to it. Now, it's got to be one of the nitrogens that isn't involved in the hydrogen bonding. So the PowerPoint will take you through some highlighted things for that. But these bits of the molecule, this end, whoops, didn't mean to do that. This end of the molecule is all involved in the hydrogen bonding that gives our double helix. It's holds it together. So this one and this one are some of the ones you'll be highlighting as the guanine atoms, because it is guanine that's involved here, that can form a dative bond to the platinum. So here's our platinum ready to form that dative bond. And I'm going to do a bit of jiggery-pokery here now. There it goes. So there's nitrogen, and here's my platinum. And with a bit more, bear with me here, once that bond has formed, that's a ligand substitution. Once the guanine started to act as a ligand, my other guanine residue from somewhere else in the molecule comes along, and one of its nitrogens, either this one or the other one, this one at the top. I know it's not quite working. Or this one at the top. That's still not working. Never mind. Forms another dative bond. There we are. I'm going to give up on this in a minute. There it is, kind of. So that will form a kink in the chain. Now one thing you need to know is why from this diagram does transplatin not do this? So transplatin is similar to this, of course, but we've got these bits swapped over. In fact, do I have a transplatin to show you? Kind of. There it is. There's my transplatin. So it's not the right shape to cause that kink. It's not the right shape to bond to those guanines in a way that can then have two guanines sticking together to form the kink in the chain. You can't quite see that from the diagram, but you just need to be aware this shape doesn't allow this to happen.